Time for another draftphysics.com, debatephysics.com also, but there's just nobody to talk to. Scientists are terribly, weaselly, cowardly, creepy, arrogant, fucktarded assholes, unfortunately. So that's the only conclusion to draw, just because I've asked so many to engage in the conversation and they just won't do it. And it's really irritating. Because they won't take any chances. They all don't, they all are completely unsatisfied. I mean, they are unconfident. Okay, they're pretending they have all this confidence, but they don't have any confidence. And that's why they won't really talk about any of these subjects, is because the fact is they really don't know answers. They don't have answers for why. And they're afraid to make a mistake. That's simple. So anyway, I was, it's so obvious that gravity makes things hot because it causes pressure. Pressure makes things hot. And it's just so obvious that things don't stop accelerating when they hit the Earth's surface. If I drop something and it hits the Earth's surface, it doesn't stop accelerating. I mean, it makes heat right on the surface, its impact, but it's material bits. Even if they break into a million little pieces, it's still a million little pieces, and they're still accelerating in gravity. They're still collecting gravitational momentum, the same momentum they had when they're falling. They still are collecting the 9.8 meters per second if they're on the surface of the Earth. And they're still collecting it. They're still collecting it. They're still collecting it. They're still moving. All right, technically. They're pushing and then they're pushed back, and they push and they push back, and they're pushed and they're pushed back. So there's a tremendous amount of energy or pressure going that way. So I guess the reason why they can't recognize something very simple, I ask a simple question: why is the Earth's core molten? And their answer is nonsense. They're blaming well, I'll get to what they're blaming. But the point is they're not blaming gravity, which is the obvious answer. It's just so obvious. Now, even if you believe that gravity is a bent geodesic, it should be obvious that gravity creates momentum, movement, and that momentum has to go somewhere. It can't just disappear. And I guess the real problem is they can't concede that gravity creates momentum, because if they concede that, then they breaks conservation of energy, and they'd have to concede that the universe is getting hotter and hotter because it's constantly creating this momentum from a bent geodesic that isn't fueled by anything. There's no theory explaining how the bent geodesic gets its energy. So they can't put gravity in the physical universe of forces and recognize that it has to be accounted for like anything else. If it's causing motion, it has to get the energy to cause the motion from something. And they're not going to concede that's part of the equation, because they believe in some relativistic space-time warping nonsense that magically creates the motion. And so they can't account for it and then believe in conservation of energy, or believe that the universe is any kind of steady state. And certainly it's exactly opposed to their silly theory about entropy, as if the universe is getting colder, when obviously the universe would have to be getting hotter and hotter if it's getting this free momentum put into it, free heat. And the heat has to go somewhere. Okay, So anyway, all right, so I'll read this silly AI explanation. That's pretty much a composite of the scientific opinion. So somebody did post a comment, appreciate it, quoting some of this kind of style crap. And, it's just that. It's just made up crap. So anyway, the Earth's core is composed mainly of iron and nickel. It's obviously going to be composed of heavier elements because, frankly, it's the gravity thing. The heavy stuff's going to sink. It's not as buoyant. All right. The molten is molten in the outer part and solid in the inner part. So we know that it's not solid in the sense of a temperature solid. It's not solid naturally solid. It's solid because it's not being allowed to expand and turn into a liquid. So you shouldn't think of it as solid like ice is solid, because they've changed the temperature at which it can go from being a solid to being a liquid by applying pressure. So the pressure is really deciding, not the temperature. So you shouldn't be confused that somehow because it's solid it's colder. Now it can still be very, very hot, it's just under higher pressure. So it's just like water boils at a much lower temperature the higher your altitude, which means the lower the pressure. And the higher the pressure, the higher the temperature at which water will boil. This state of matter is maintained by a delicate balance of extreme heat and intense pressure, and it's constantly leaking to the surface, so it is escaping. So the point is that we can't make any perfect vessels to even, insulate something. There's no such thing as a perfect thermos. So there's no, they all leak. It's just a matter of time. How much you can slow it down by making the conduction weaker and weaker and reflecting as much of the radiant energy as possible. But you still can't change the fact that if you hit a mirror, you're going to heat the mirror. Even though it's reflecting most of the photons, it will get hot. Eventually, it's going to get the same temperature as the environment that's hitting it, and so it will radiate the heat eventually. It's just harder for it to do it, but you can't make it so it doesn't happen. You can't stop the photons. You can't stop the radiant energy. All right, anyway, extreme temperatures. The Earth's core is incredibly hot. The temperatures are estimated to be between 4,000 and 5,000 Kelvin. At the outer part of the core and even higher in the center, comparable to the surface of the sun. These high temperatures are a combination of, and it says, leftover heat from planetary formation. Now this is the dumbest of all the answers. We're talking about 4 billion years ago, where this bombardment was anywhere near significant, let's say. It's just preposterous that 4 billion year old heat is still stuck in the Earth. It's just a silly thing to say. There's no way it could last that long. There's no way it wouldn't radiate out. It's just a nonsense statement. I can't believe they say it. All right, the formation of the Earth involved countless collisions and released an enormous amount of gravitational energy. Now, isn't that the joke? So they're calling it gravitational energy, but they're basically saying gravity can't cause energy, because then you can create free energy from gravity, because there's no source feeding gravity. There's no energy going into the bent geodesic. So the whole thing is just nonsense, circular crapola. Let's see, which generated immense heat. So it's they're saying it released enormous amounts of gravitational energy, and you're just saying, what are you talking about? Collisions? Released gravitational energy? No, they're just momentum arguments, right? So you're just saying these things had velocity for lots of different reasons, and gravity wasn't the only one. Like a meteor, it's not just about gravity that gives the meteor. Obviously, the sun is pulling on it. Lots of things can happen that it's in an orbit, but its original velocity might be from an explosion. Obviously, you could argue that was stored gravitational energy, but it's just reaching. So anyway, it's just a silly answer to the question. To speculate that, and let's understand that the temperature of the Earth has been relatively stable. The interior temperature had to be relatively stable over the last at least billion years, because life wouldn't exist otherwise. So it had to be a rather stable. I mean, obviously the surface temperature is partly controlled by the internal temperature, but it's mostly being controlled by the sun. So in the atmosphere, so there's no real room for some idea that the Earth is slowly cooling or any of that kind of crap. It really can't be. It had to be at a pretty stable temperature to maintain the conditions that exist. All right, the formation of the Earth involved countless. Oh, I already did that, right? Yeah. All right, radioactive decay. Now that's really dumb too, I'm saying, because we're talking like some of these isotopes, like uranium, what is it, 10,000 years half-life. So every 10,000 years, there's half as much uranium. So you got to say, well, wouldn't that mean that over time you have less and less and less of this material to decay? So unless you have some theory that it's creating uranium somewhere, it clearly over 1 billion years, okay, the temperature would have to decrease because the concentration of the uranium would be declining constantly, and there would be half as much of it, and half as much of it means it's going to have less and less capacity to maintain a chain reaction and create any kind of heat. So that seems like a completely bogus answer to the question. It really can't be about radioactive isotopes because the time scale says that can't work. I don't think the time scale says, how can I make it work? How can I make the idea that the uranium is inside the core of the Earth and half of it is inert every 10,000 years? I mean, it just doesn't, how can I make that make sense? All right. So anyway, that's just too silly. So radioactive isotopes like uranium, potassium within the core and mantle continually generate heat, and somehow at a constant rate. So even though their half-life, they're decaying, their energy is being spent, somehow what's refueling the nuclear power plant? Who's putting new uranium into the mantle of the Earth? I mean, if it was a nuclear power plant, you'd understand. Yeah, it gets degraded. Just use it up. And you change the half-life, right? I mean, the whole point is that you're putting the uranium in close proximity and you're decreasing the half-life significantly. That is, you're causing more accelerated decay. So it decays much faster than that 10,000 year number gets changed to like 5,000 or 2,000 or 500 years or some other number. While estimates vary, radioactive decay is thought to contribute significantly to Earth's internal heat budget. So again, it can't be the right answer because it would be way too variable and the Earth would be getting slowly, well, not even that slowly, every 10,000 years it would be getting, if it was all created by uranium or some isotope, every 10,000 years it would be getting half the temperature. It would be getting that much colder. So that's a silly answer. Okay, frictional heating. Now this just, you're just like, duh. Okay, the movement of and sinking of denser materials. Now, they're only moving because they're able to realize their gravitational acceleration because they're heavier than the objects around them, so they're going to create a buoyant reaction. Okay, they're going to sink lower than the lighter things they're in contact with. And so they're just realizing their gravitational acceleration and actually moving. So instead of transferring it, instead of not being able to go, so it's bouncing, they're able to go. But bouncing and going are the same amount of heat. So it doesn't matter whether they move or they bounce. It's going to be the same amount of motion in the end. There's not going to be a different amount of motion. The acceleration has to be absorbed by the Earth, or it is absorbed by the object and it moves. So there's only two choices. Like I said, when you're sitting on Earth, you're still falling into the Earth. You haven't stopped pushing into the Earth, okay? You're still drilling a hole in it, so to speak. And yes, it's because of its pressure, it's pushing you back. That's what's happening. But it's all motion. You haven't undone any motion. That's why it becomes hot. And it's because you do have a lot of motion. You're moving other atoms. You're transferring the motion to other atoms. But it's all motion, and you can't undo the motion. Okay, so anyway. Denser materials, including iron to the core, also generate heat through friction. So again, that's obvious that everything is creating friction in the sense that everything is pushing on other matter and conveying, okay, through conduction, its heat. So the pressure is essentially just conductive heat. All right, pressure influence. Let's see what that says. Despite the incredible high temperatures, the inner core is solid due to the overwhelming pressure. So that's just an argument about how pressure and temperature have to be understood working together to decide when something goes from solid to liquid. So pressure increases the temperature you need to make something liquid from the weight of the overlying layers. So obviously they're conceding. What is the weight? The weight is momentum. So again, this is, I mean, it goes back to so many of these arguments, but I mean, it's just sort of a duh statement that what is weight? Weight is momentum. I can duplicate weight. I got my scale here somewhere. Where the hell is the scale? Anyway, I just take a scale and turn it sideways, okay, and I push something into it. I can duplicate its weight with a velocity. I can create exactly the same thing as weight, all right, in terms of an impulse. And I can do it with my finger. I could create the same pressure, okay, being constantly applied by just pushing my finger into a scale and creating a number, and that number is the amount of pressure I'm applying to the scale. So clearly weight is the same thing, okay, as pressure. The overwhelming pressure from the weight of the so it's like saying the overwhelming pressure of the pressure, or the weight of the weight of the overlying layers. Yes, the weight, their acceleration, their motion. This pressure increases the melting point of iron, causing it to solidify. So that's just the point. It is obviously, yes, this will happen. If you can make something a high enough pressure, then it will condense, okay, into a solid. However, the pressure in the outer core is not as high, allowing the metal to remain in a molten liquid state even though at these high temperatures. So, you know, what the boiling point is, or however you want to describe it, the liquefying point. And you're going to have all kinds of convection and conduction. But the point is that you can't contain heat. There's no container for it. Especially there's no natural container. Nature doesn't make thermoses. All right, so no body could have heat inside of it that just stays inside of it and doesn't go anywhere. It always goes. High pressure always goes to the lower pressure, and so eventually you're going to excrete it to the external world as radiant heat. You can't avoid the fact that you're going to create radiant heat, and you're going to lose your heat as photonic energy in the environment. In essence, the molten outer core is a consequence of the Earth retaining immense heat from its formation. So again, that's just a silly argument. Replenished by ongoing processes like radioactive decay, which again doesn't make any sense for a consistent planet, and a planet that has had a consistent environment, relatively consistent for billions of years, while the pressure environment is yet not high enough to force material into a solid state like the inner core. And whether it's in a solid state doesn't matter, right? The inner core is not cold because it's a solid. It's hot as hell. It's just being forced not to liquefy, but it's still got an insanely high temperature. All right. So that's all just really bad science, in my opinion. Everybody should agree that's pretty crappy. They didn't really think any of that stuff through, and these are supposed to be good enough answers. They'll teach a kid this nonsense and be satisfied that they've, you know, done the truth some honor, and they really haven't. All right, so I'll do a little bit of drawing, I guess. Yeah. But it's just a simple enough argument, and so again, it just defeats the whole idea of this idiotic notion that there's something called a bent geodesic that causes gravity, that it's somehow this warping of space can somehow cause momentum and give things the capacity to create heat. It's just too stupid. People just let it go. It's just too stupid. Alright, so back. So again, bent geodesic. So let's just say, okay, if you believe in anything that causes motion, you've got to understand that what that's basically going to look like, right? I mean, they teach relativity theory by actually talking about a fluid moving, you know, anti-convergence is what they call it, right? Because they don't want to say the word convergence, but it's a convergence, and it's just the opposite of a light bulb. It's the inverse square law, and you're basically just saying that there's elements and they're converging onto the Earth from all directions, and that's bent space, and that's how it works. And so you got to say, of course, it's going to get hot in the middle. It's going to be the opposite of a light bulb in the sense that instead of radiating the heat, it's going to be, collecting the heat. And it doesn't seem complicated at all. All right, so my basic premise is there's, the two forms of matter. So we'll do matter in blue and force in red. And the idea is that the electrons and protons are the matter, and the fact is these little discrete bits of these quanta, as Einstein would put, of energy, they carry momentum. So we know that a laser beam, it's hot. You can burn things with it. You can push things with it, quite frankly. It carries momentum. And so, the idea that the universe is full of this photonic energy, okay, in different forms that we can see and not see, and that it's constantly going in all directions and in all places in the universe. But the fact is the only ones that are going to be relevant to a material body are the ones that are going to collide with it. So obviously the ones that are going in some direction like this and aren't going to hit it, well, they're irrelevant. And so the only stuff that's going to have contact with it is stuff on some sort of straight line path, and you just end up with a perfect radiator, right? In the end, you got a material thing that's just you could just understand that's what it's going to look like, as a little spiky thing. And there's a preposterously large number of spikes, but the idea is you could just say, well, we'll just represent each one of those spikes represents 1,000,000 spikes, and it doesn't really matter. So anyway, so what's so hard to understand? That yes, gravity is a real force, and it's made out of this speed of light energy that's in the universe. We already know is in the universe. Okay, so they give a total for the microwave energy being about 2 Kelvin worth. Okay, and I would argue in the dark side, the coldest place on the moon is 50 Kelvin, or well, it's actually colder than that. It's 27 Kelvin or something. So anyway, so I think we already know that, yes, the real cold number is higher than 2. Okay, there's more photons, there's more something in the universe than just that 2 worth. There's something closer to this 30 to 50 kind of number. I mean, they say the coldest place on Pluto is 50. Which doesn't make much sense. How does the moon get colder than Pluto, right? No, it doesn't make any sense. So anyway, so the point is that, look, this diagram works, of just understanding that, yes, there's photons out here in the universe. They're going to hit the matter. When they hit the matter, the key thing that's going to happen is the little bit of energy was going the speed of light, okay, before it hit the matter, and then when it's pushing the matter, it's only going this tiny speed, okay, or smaller speed, 10% to 100%, and 1/100th of a percent, that kind of thing. And so it's in a sense lost some of its energy, in the sense that it's going to have fewer collisions in the universe. It's going to do fewer transfers because it's not moving as fast. It's not covering as much territory. But it is moving as a bigger object, so it's going to have more interactions in that sense. But anyway, it's obviously occupied pushing the matter. And that's what is happening inside the Earth, is that each time this force hits something, so we know that, look, it's something falls in gravity, and we already know it's a time-dependent force. It's how long it's in the gravity. So if I shot past the gravitational body, if I go very fast, I'll be bent very, very slightly, and if I go very slowly, then I'll crash right in. Indicating clearly that, yes, this is an external pressure. It's pushing. It's a wind blowing, and the faster I go through the wind, the less the wind moves me, and the slower I go, the more. Paint sprayer. I'm going in front of a paint sprayer, right? The faster I go through the paint spray, the less paint gets on me. And that goes for going forward and back also, right? So if I'm going with the paint spray, the spray's going faster than me, but I'm going to move away from the paint sprayer. It's going to change how much spray hits me the faster I go. So the faster I get away from the paint, the less paint that's ultimately going to hit me because of that inverse square law. There's less and less density of it further and further away. And this is just the opposite circumstance, where there's more and more density the closer you get to the Earth. And we know at the surface here it's this 9.8 meters per second, not per second square, per 1 second. In 1 second you get 9.8 meters of acceleration, which means your velocity, if in free fall, will be 9.8. But you won't travel 9.8, you'll travel, as Galileo said, 16 feet. Okay, so 4.9 meters. But regardless, we know that's what you get added each time. Each second, you only get that 4.9 added. That's the added distance, and you only get 9.8 added. And so your velocity, 4 times the height, only twice the velocity, only twice the time and the gravity, blah, 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 blah. So obvious that it's nonsense to say something has twice the energy when it has 4 times the energy when it only fell for 2 units of time in gravity. You can't get 4 units of energy from 2 units of force. Anyway, so it's just kind of obvious it's always pushing, so the photons are always pushing, and it doesn't, if they can't make the object move, okay, there has to be a reason it didn't move, because frankly you hit it with momentum, so there has to be some opposing momentum that's stopping the motion, and all of that has to happen as a real event. That is, you can't stop this object by merely hitting it. You have to get rid of all of its momentum. You have to stop it and then reverse its direction. So obviously each time something hits a force, it has to get rid of all of its momentum. So all of it has to be returned to free, instead of being stuck on something. And then to reverse its direction requires the absorption of force. It has to absorb force again. So it's it's just obvious that these little bits of discrete energy in the universe are just being transferred from being in this free state to being in this state where they're pushing on bits of matter. So obviously as you go deeper and deeper into the Earth, the amount of pressure, force, gets higher and higher, because each one of these things is carrying that force, carrying a momentum, and all of that momentum adds up and adds up and adds up and adds up. Now obviously though, it can't not go somewhere, so this stuff going this way eventually, pops out this side, and the stuff going in this way obviously eventually pops out this side, but it's eventually. So at any one moment of time, at this exact moment of time, the stuff, if I'm out here and I'm saying, well, the force on this side is eventually going to reach this other side, well, it's not going to do it now. It's going to do it eventually. So I'm stuck in a differential because there's less coming out than is going in. And that's a fact. So at this exact moment, there's less coming out of the Earth than went into the Earth. But a moment later, it would catch up. But we don't have it. It's not a moment later. It's now. I can't exist any other time than now. I can't exist later. And if I wait till later, then there's more force coming this way that's going to be hitting me, so I'm not going to be free from the problem. And the problem is just you're constantly fueling the heat inside the Earth. The Earth isn't just hot from some previous event and it's just slowly radiating its energy. It's constantly being fueled by the pressure being applied by all of the accelerating tiny electrons and protons and atoms, all moving towards the center, all being pushed towards the center, whether they move there or not, all being accelerated towards the center. And all of that motion has to be dissipated. And so it's dissipated as pressure the opposite way. The stuff going this way ends up being stuff going out. So it starts off creating pressure and then it leaves releasing pressure. But obviously it's taking time to do that, and that time differential, the time you've absorbed the force and not allowed it to get where it was going, so to speak, is the differential that keeps accelerating things towards the center. So it ends up being conservative in the end, but it's not conservative at any exact moment in time, because you're always I don't know if I can do it on this page with all this other stuff. The point is that you're really just, the only thing that's changing in the universe, you could argue, is that there's an amount of force that's free, okay, flying around in the universe, and then there's an amount of force that's trapped pushing matter. And that differential defines the gravitational constant. If you broke all the matter and released all of the force that was giving it momentum, that is, you released the matter and it stopped moving, okay, so it no longer was occupying force, then the gravitational constant would increase, because you've put a bunch of force that was moving slow back to being force moving fast in the universe. So it can apply more pressure because you released more force to the environment to create the pressure. So you could argue that matter is an energy sink, in a way, that energy goes in and doesn't immediately come out, and that creates what we call gravity. Alright, I think that's enough, but we'll think about it and see if that's all I want to say. I mean, it's just this idea is just to understand that it's all the motion is caused by force, and the matter moves when it's forced to, and it can't move in both directions at the same time. So obviously it has to go through the process of moving in a direction, being stopped because more force comes from the other side, and then being pushed the other way. And it's not about, there's no, I did a previous video on drag. There's no such thing as drag, but you can't change how much force is on one side and how much force is on the other side. You can just change when you hit the force. So that's another thing to understand, is all these collisions are speed of light collisions. And you're really just saying that you have something that's going the speed of light and now it's pushing matter. And when element of energy hits from this side and say reflects, and then this piece bounces off, it's just a speed of light collision. It doesn't matter how fast the matter was going. The only thing that matters is how fast the force will go when it's released, and it's just going to go the speed of light. And so that's the constant. So it doesn't matter how fast this matter is going. It can't make this collision can't be any more potent. It can only kinetically do one thing, and that is like two steel balls hitting each other. It doesn't matter how fast they're going. They're always going to, so to speak, reflect completely. And that's all that can happen here, is the force bit reflects completely, and this one reflects completely. So it doesn't matter how fast this matter's going. And so all you're saying is I have a certain amount of energy on this side, and if I go into it sooner, well, that's all I'll do is hit it sooner. It was inevitably going to hit me anyway. I just plowed into it sooner, right? So I haven't defeated the energy behind, right? So I went ahead of the energy behind me. And so now there's still a bunch of energy behind me that when I stop will catch up to me and hit me. So I'm just going to regain my momentum. I can't undo. If I get extra push from one direction, I can't undo that. Okay? Drag can't stop it because there is no technical drag. All you're doing is changing the timing. So technically everything in space, when it's moving, moves, is sort of dragged to a stop, but then the energy catches up, okay, and it moves again, and then it stops, and then it moves again, and then it stops. So it's just stuttering on its path. So there is technically drag, but the drag is only temporary, I guess you could argue, and it's the equilibrium can't be broken. So the only way you can stop something from moving once you've caused it to move is you have to add another piece of energy in front of it. You have to add an opposing piece of energy to actually stop it. stop it permanently. You have to equalize the pressure. So until you equalize the pressure, moving can't change the pressure. So if I make more pressure over here, I'm stuck with it until I make more pressure on this side. Yeah. So pause and we'll see if there's something to add. Alright, so a correction. So I basically said pressure, I think, equals heat, and it's kind of wrong to say because of the whole idea of conduction and the fact that you can create a circumstance where the material conducts heat, alright, very efficiently. And so it's basically taking a force that hits it on one side. So I could do that with like a steel bar, I suppose. And you could argue that I could do a Newton's cradle and I could hit it and I could have a ball on the other side and it'll fly off. But the longer I make that steel bar, let's say, the less efficient it gets in conducting, okay, the energy. And you'd say that you're going to get less and less depending on the length of that piece of conducting material. So same is true for electricity. The superconductor works because there's fewer of these impurities and there's less motion in the atoms going the wrong way. So if they're not jiggling this way, then they can't change the energy going this way into energy going that way. So it maintains, it conveys the force very efficiently. So at the speed of sound, the force of this impact, okay, the pressure, will be transmitted to this other side and create an action. And so there's less of this delay thing I was talking about because you're not moving as much material. You're just jiggling an electron, and then the force is pushing the other electron, and that's pushing the other electron kind of idea. So I guess in this case you could even think of the atoms being moved a little bit, and so they convey that little tiny bit of motion to the other end, and the other end hits the object and moves it. So the more conductive the material, okay, the pressure doesn't necessarily mean heat. It just means the heat is transferred more efficiently from one side to the other. So you could make that argument that the Earth's core is hot in the sense that it has a tremendous capacity to expand. So you can, it's like liquid nitrogen. You could argue that when you convert it from a liquid into a solid, into a gas, that what you're doing is creating real motion in the molecules, extra motion, and that can only be created by absorbing what would be force. So there's very little force trapped in between when it's in the liquid state, and therefore when you convert it into the gas state, it takes away, okay, it consumes more force and lowers the temperature. Because the other stuff can't be moving as fast because it's moving more stuff. It's moving more stuff a higher velocity. You could argue that. So it's carrying more force because it's moving at higher velocities. Yeah, that would be probably the better answer. Regardless, so it's sort of a latent heat argument that solids can hold latent heat because you've pressurized them into being a solid, and they have a capacity to, expand if the pressure is reduced. And when the pressure is reduced, you'll use the latent heat. Something like that, maybe. Okay, it needs a little work. Yeah, so we'll work on that part. So it is the trick is that pressure, we know, like in a cylinder in a car, it creates heat, but in the especially when you're pressurizing, so the process of pressurizing, so if you want to make liquid nitrogen, you have to pressurize. The process creates a lot of heat, so pressurizing creates heat. So you would argue that the Earth is constantly being pressurized, in the sense that the pressure is constantly being used and then reversed, and then used and reversed, and used and reversed. So it's constantly pressurizing and then releasing that energy. So it's in a constant condition of being pressurized, released, pressurized, released, pressurized, release. That kind of thing, I guess. So it's constantly hot because you're always doing the pressurizing cycle. Maybe. Anyway, okay, so probably enough. So till the next time, and such, and so forth, and whatnot. Draft video.